Feature resolution R in lithography is fundamentally limited by the Rayleigh criterion. R equals K1 times lambda divided by numerical aperture. To achieve sub-10 nanometer features, the wavelength lambda must drop drastically below the 193 nanometers used in argon fluoride immersion systems. Extreme ultraviolet lithography, or EUV, achieves this by utilizing a nominal wavelength of 13.5 nanometers. This specific wavelength corresponds to photons carrying approximately 92 electron volts of energy. The choice of 13.5 nanometers is not arbitrary. It maximizes the reflectivity of molybdenum silicon multilayer mirrors. These mirrors exhibit their peak reflectivity, around 70%, precisely near this spectral point, enabling the necessary reflective optics for pattern transfer. Extreme ultraviolet light generation relies on laser-produced plasma sources. A high-power carbon dioxide laser pulse, typically operating between 20 and 30 kilowatts, strikes microscopic droplets of molten tin. The laser ablates the tin material, instantly creating a high-temperature plasma. Tin is specifically utilized because its ions, ranging from SN8+ to SN13+, emit intense radiation centered exactly at 13.5 nanometers. This emission occurs via unresolved transition arrays. Currently, the conversion efficiency from the input laser energy to usable 13.5 nanometer light remains low, approximately 5 to 6%. Effective debris mitigation systems are essential to protect the collector mirror. These systems often employ a flow of hydrogen gas to stop high-velocity tin atoms and ions from damaging the critical reflective surfaces. Standard refractive optics are unusable at 13.5 nanometers because all materials exhibit extremely high absorption coefficients at this wavelength. Consequently, EUV systems rely entirely on reflective optics. These mirrors function based on the principles of Bragg reflection. Each mirror consists of 40 to 50 alternating layers of molybdenum and silicon. The precise layer pair thickness, denoted as D, is controlled to approximately 6.9 nanometers. This thickness satisfies the Bragg condition, 2D sine theta equals m lambda, specifically for near-normal incidence, where the angle theta is approximately 85 degrees. While the reflectivity of a single molybdenum silicon interface is inherently low, constructive interference across the 80 to 100 interfaces achieves the required peak reflectivity near 70%. The EUV imaging system typically employs 6 reflective mirrors to project the mask pattern onto the wafer surface. The system resolution is directly proportional to the numerical aperture, or NA. Current production tools operate with a numerical aperture of 0.33. Increasing the numerical aperture improves resolution but simultaneously reduces the depth of focus, or DOF. The depth of focus is inversely proportional to the square of the numerical aperture. The K1 factor quantifies the process complexity. Achieving lower K1 values, typically below 0.3, mandates the use of complex resolution enhancement techniques. These techniques include source mask optimization and aggressive optical proximity correction to ensure pattern fidelity. High wafer throughput in manufacturing requires substantial extreme ultraviolet source power. The typical target for high-volume manufacturing is 250 watts of intermediate focus power, necessary to achieve a throughput of 170 wafers per hour. Attaining this power level demands extremely high laser driver power and maximizing the conversion efficiency from laser energy to EUV light. Power scaling introduces significant thermal management challenges, particularly in the collector mirror. The collector absorbs substantial out-of-band radiation and heat generated by the plasma. Furthermore, collector degradation occurs due to sputtering caused by high-velocity tin debris, which reduces reflectivity over time and necessitates frequent maintenance cycles. Standard refractive optics are unusable at 13.5 nanometers because all materials exhibit extremely high absorption coefficients at this wavelength. Consequently, EUV systems rely entirely on reflective optics. These mirrors function based on the principles of Bragg reflection. Each mirror consists of 40 to 50 alternating layers of molybdenum and silicon. The precise layer pair thickness, denoted as D, is controlled to approximately 6.9 nanometers. This thickness satisfies the Bragg condition, 2D sine theta equals m lambda, specifically for near-normal incidence, where the angle theta is approximately 85 degrees. While the reflectivity of a single molybdenum silicon interface is inherently low, constructive interference across the 80 to 100 interfaces achieves the required peak reflectivity near 70%. The EUV imaging system typically employs 6 reflective mirrors to project the mask pattern onto the wafer surface. The system resolution is directly proportional to the numerical aperture, or NA. Current production tools operate with a numerical aperture of 0.33. Increasing the numerical aperture improves resolution, but simultaneously reduces the depth of focus, or DOF. The depth of focus is inversely proportional to the square of the numerical aperture. The K1 factor quantifies the process complexity. Achieving lower K1 values, typically below 0.3, mandates the use of complex resolution enhancement techniques. These techniques include source mask optimization and aggressive optical proximity correction to ensure pattern fidelity. High wafer throughput in manufacturing requires substantial extreme ultraviolet source power. The typical target for high-volume manufacturing is 250 watts of intermediate focus power, necessary to achieve a throughput of 170 wafers per hour. Attaining this power level demands extremely high laser driver power and maximizing the conversion efficiency from laser energy to EUV light. Power scaling introduces significant thermal management challenges, particularly in the collector mirror. The collector absorbs substantial out-of-band radiation and heat generated by the plasma. Furthermore, collector degradation occurs due to sputtering caused by high-velocity tin debris, which reduces reflectivity over time and necessitates frequent maintenance cycles. Extreme ultraviolet masks operate in reflection mode, making them highly susceptible to particle defects. A particle resting on the mask surface creates a shadow defect when projected onto the wafer. Unlike deep ultraviolet systems, EUV requires a protective membrane, known as a pellicle, to shield the mask from airborne particles. The pellicle must exhibit high transparency to 13.5 nanometer light, ideally exceeding 90%, while remaining mechanically robust enough to withstand heating from the high-power EUV beam. Current production pellicles are typically fabricated from thin carbon nanotubes or amorphous silicon membranes. These achieve approximately 83% transmission. Pellicle heating is a critical concern, as it causes thermal expansion and potential distortion of the projected pattern. To enable feature scaling below 8 nanometers, the semiconductor industry is transitioning to high numerical aperture extreme ultraviolet systems, operating at 0.55 Na. Increasing the numerical aperture necessitates larger optics and fundamentally changes the magnification scheme. High numerical aperture systems utilize anamorphic magnification, a 4 times reduction in the scanning direction, designated Y, and an 8 times reduction in the static direction, designated X. This anamorphic approach requires larger mask blanks and reduces the usable field size on the wafer. Consequently, 2 separate exposures, a process known as stitching, are required to cover the standard chip area. The increased numerical aperture significantly tightens alignment tolerances and drastically increases the complexity required for aberration correction. Extreme ultraviolet lithography is now fully integrated into high-volume manufacturing for 7 nanometer and 5 nanometer technology nodes. Future scaling relies on high numerical aperture EUV systems for the 3 nanometer and 2 nanometer nodes, potentially followed by hypernumerical aperture systems exceeding 0.6 Na. At these extremely small feature sizes, stochastic effects become the dominant challenges. These effects include line edge roughness and photon shot noise, resulting from the limited number of photons available per exposure area. Further advancements require the development of highly sensitive photoresists and improved dose control mechanisms to effectively mitigate these inherent statistical variations.